Alright, let's discuss this a little bit before we get into any formulas. Dams are thicker at their bottom than the top because the pressure increases with more depth. The pressure at any point on a dam depends only on how far below the surface the point is, and not on how much the surface of the dam happens to be tilted at that point. The pressure in pounds per square foot at a point h feet below the surface is always 62.4 times h, where 62.4 is the weight density of water in pounds per cubic foot. The pressure h feet below the surface of any fluid is the fluid's weight density times h. So we get this pressure depth equation. In a still standing fluid, the pressure P at depth h is simply the fluid's weight density W times h. So the pressure would just be W times h. Okay, now, so for a constant depth formula, we will use the equation pressure equals the weight density times h to derive a formula for the total force exerted by a fluid against all or part of a vertical or horizontal containing wall. In a container fluid with a flat horizontal base, the total force exerted by the fluid against the base, so we're talking like a soda bottle and the contents, the pressure on the bottom of the bottle, can be calculated by multiplying the area of the base by the pressure at the base. And so we can do this since the total force equals the force per unit area times area. So if F, P, and A, where F is the total force, P is the pressure, and A is the area, then the force is equal to the force per unit area times the area of that particular wall. So fluid force on a constant depth surface is force is equal to P times A, or WH times A, where W is the weight density, H is the height of the depth, and then A is the area. Okay. So here's an example. Suppose these are two circular containers, and suppose they have the same area down here on the base. So basically what I'm saying is they have the same area here. So basically they have the same circular area down there. Okay. And so if we were to fill the containers with the same fluid to the same depth, the total force on the bottom of each container will actually be the same. Okay, so it doesn't really matter the shape of the containers, but as long as they have the same area on the base. Now, a fluid's weight density is actually its weight per unit volume, and that's usually in pounds per cubic feet. So some common weight densities, and we've already talked about water being 62.4, is gasoline is 42, mercury is 849, milk 64.5, molasses 100, olive oil 57. So since the weight density of water is 62.4 pounds per cubic feet, we can find the force on the bottom of a rectangular pool. So in other words, the force of the water, if we have a rectangular pool that's 20 feet by 30 feet and 5 foot deep, then we simply take the area, which is 600, multiply it by the depth, which is 5, and then multiply it by the weight density of water, which is 62.4, and that gives us a force of 187,200 pounds. Similarly, if we had a can of gasoline with a circular base with a radius of 0.5 feet, and it's filled to 1.5 feet, then we would have, let's see, the area would simply be pi r squared, so it would be pi times the radius squared, and then multiplied by the height, which is 1.5 feet, and then multiplied by the weight density of gasoline, which is 42, and that'll give us 49.48 pounds. Now for the next paragraph says, for a flat plate submerged horizontally, like the bottom of a swimming pool that we just discussed, the downward force acting on its upper face due to the liquid pressure is given by this formula that we just covered. Now, if the plate is submerged vertically, however, then the pressure against it will be different at different depths, and the equation F equals WHA is no longer usable in that form because H varies, because the height varies. So, at different depths, the pressure on a vertical wall would be different. So by dividing the plate into many narrow horizontal bands or strips, we can create a Riemann sum whose limit is the fluid force against the side of the submerged vertical plate. And so now we'll talk about that procedure. So suppose we want to know the force exerted by a fluid against one side of a vertical plate submerged in a fluid of weight density W. Okay? So that's what so here's a picture here. Now this plate is submerged vertically, so you're actually kind of slicing that plate through the fluid. So think of it like just a plate, like a big giant plate there, and so we want to know the water pressure on that plate. So anyway, to model it, to find it, we're going to model the plate here as a region extending from y equals a to y equals b. So it goes from y equals a, the lower part of the plate, to y equals b, the upper part of the plate in the xy plane. And so we can partition a to b like we normally do into strips. So let's just take a horizontal strip right here, okay, and these are perpendicular to the y-axis. So the typical strip from y to y plus delta y, that would be from the bottom of the strip to the top of the strip, is delta y units wide. So the height or the width of the strip would just be delta y. And it's how long it is depends on some function of y. So the length of it would go from here to here. So that'd be the length of it. So we'll assume that this length function is going to be a continuous function of y. So now the pressure, it actually varies across the strip from the top to the bottom. So the pressure here would be different here, 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 and so forth. The pressure would vary. So if the strip is narrow enough, however, the pressure will remain close to its bottom edge value of Wx, the strip depth. So the force exerted by the fluid against one side of the strip will be about the pressure along the bottom edge of the strip. So pressure along the bottom edge of the strip times the area of the strip. Okay, so that would be, what would that be then? So that would be the density, whoops, sorry about that. So I hit the wrong button there, sorry about that. So that would be the density of the fluid times the depth of the strip, okay, then times the area of the strip. And remember, the area of the strips is just the width of the strip, delta y, times the length across of the strip. So, whatever this distance from here to here is. Okay, so now that we have delta F, we can now evaluate an integral to get a formula for F. And that's going to be the next theorem here. So the integral force for a fluid force against a vertical flat plate. So suppose that a plate submerged vertically in a fluid of weight density W runs from y equal a to y equal b on the y-axis. Let L sub y be the length of the horizontal strip measured from left to right along the surface of the plate. Then the force exerted by the fluid against one side of the plate is simply integrating from y equal a to y equal b. This is just the density of the fluid times the depth of the strip times the length of the strip dy. And so let's take a look at an example. So we're going to take a flat isosceles right triangular plate that has a base of 6 feet and a height of 3 feet, and we're going to submerge this vertically up to 2 feet below the surface of a swimming pool. Find the force exerted by the water against one side of the plate. Okay, so here is your triangular plate, okay, and the water level is 5 feet, and since we're submerging it 2 feet below, then the water level at the top of this triangular plate would just be 3 feet. And we know that the base is 6 feet, so that just means from here to here is 6 feet. And we know the height is 3, so we know from here down to here is 3 feet. Okay, so I've established a coordinate system here. So I just put this point of the triangle right here at the origin. So this will be the x-axis, and then the y-axis will cut it in half. Okay. Now, as I said, the surface of the pool lies along the line y = 5, the plate's top edge along the line y = 3, and the plate's right-hand edge lies along the line y = x. So this is y = x. Of course, this over here will be y = -x. Okay, and the upper right vertex is at the point 3,3. So that's just this point right here is at the point 3,3. So let's look at the strip. The length of the strip at level y is actually, we can say from here to here. Let's see, if we have y = x. Okay, so from here to here is x, right? From here to here is x. So if we go from here all the way over, we get 2x. So the length of the strip here is 2x. Now the depth of the strip would actually be, the depth, not sure what's going on here. Okay, my computer went haywire there for a minute, so I'm not sure why. Okay, so anyway, so basically the depth of the strip is just 5 minus y, where y is the height of the strip. So the height of the strip from the bottom would be y, so the depth of the strip would be 5 minus y. So finally, if we apply the formula that we talked about, we're actually going to integrate this from x = -3 over to x = +3, okay, and then the density of the water is 62.4, and the depth of the strip is 5 minus y units, and the height of the strip we're going to say is 2y. So 2x and 2y are the same value, so because of the symmetry of this problem. So the length of the strip we're just going to say is 2y. Since we're going to integrate with respect to y, I don't want to use 2x, I want to use 2y. So we integrate with respect to 2y, and then you can evaluate the integral, and we get 1,684.8 pounds for the force. Alright, to wrap this up, I'm just going to talk briefly about fluid forces and centroids. If we know the location of the centroid of a submerged flat vertical plate, ignore that figure there, we can take a shortcut to find the force against one side of the plate. The force of a fluid of weight density W against one side of a submerged flat vertical plate is the product of W, the distance h from the plate's centroid to the fluid surface, and the plate's area. So F = W h bar 8. So you could use that formula to work the previous force problem. So basically all you would do is you would say the force is W, that's the weight density of water, times h bar, which is the depth of the water level, so 3 units from the water level, and then the 9 is the area of the triangle. So the area of the triangle you can easily get using your formula, area of the triangle. And so you would get 62.4 times 3 times 9, and you get the same answer we got before. So that's actually much easier than the way we did it up there using the thin strip. Okay, so there's lots of other applications of integrals that you might run across, but hopefully this chapter gave you a whole bunch of them that you found useful.